presented by Caltech.
So now I have the opportunity to introduce Babak Hassibi, who has been at Stanford since 2001 and is actually officially a Lillian S. Bourne Professor of Electrical Engineering and has been Executive Officer for Electrical Engineering as well as Associate Director of the Information Science and Technology Initiative. And he's going to be talking about a subject that there's a lot of interest these days because of the success of deep learning networks, which is kind of a black art, and people kind of make all kinds of claims. And they evolve these different architectures, and they think there's some special kind of neural network architecture that's going to be magical, but it's actually the process by which you optimize the parameters and the architecture work together to solve the problem. It's like a whole evolutionary algorithm. So this is very complicated to understand, and I think this is going to be a very interesting talk. And it's a shed light on those kinds of dark arts that we have been practicing these days.
Thank you very much, Kwabena, for that. Yeah, I can't think of a better introduction. Dark arts is the right word, I think. And I can forgive you so there's Stanford Caltech connection. So I've been at Caltech since 2001, but I was at Stanford prior to that. So I guess that's fine. There is a strong, so we did the reverse, I think. So I've been at Stanford for grad school. I was at Bell Labs for a few years. They're wonderful places, but there's something special about Caltech. I think we can all agree about that. And this will be repetitious, but I need to thank both the organizer, but in particular Carver. And mostly because of creating the legacy that he has, and so it's something, and we've heard this multiple times before. It's something that inspires all of us in our work. But I think more importantly, it's inspired people to actively try to sustain this legacy at Caltech. And for that, I think I really need to thank the people who've supported this New Adventures Fund and do the best they can to make sure that Carver's way of thinking and his legacy, remains thriving here at Caltech. And so I think that's important. As Kwabena mentioned, I'll talk about deep learning. I'm a little embarrassed to talk about deep learning for the reasons that he mentioned. But nonetheless, that never stops someone from doing something. And I'll talk about something that I call the blessing of dimensionality. You've probably heard of the curse of dimensionality. So this is a term that I think is beginning to pick up, and I'll try to talk to that. And I should acknowledge that this is joint work with two of my graduate students, Naveed and Shaheen, and they were partially supported through funds from the New Adventures Fund. Let's see if this, okay, so deep learning. So I'm not a machine learning person. I did some neural networks in my graduate student days. I'm old enough. This was the 90s, and so in the 80s and 90s, neural networks were all the rage. Not as much as they are now, but they were all the rage back then. And so, there is no denying that deep learning has had tremendous success, right? It's influencing, image recognition, computer vision, speech understanding, and all of these kind of things. One cannot deny that. But, to someone like myself looking from afar, this was very surprising, because when I would probe people as to what they were doing, there really isn't a whole lot of new ideas since the 90s. There are these multi-layer perceptron type things. Okay, there's more layers. That's why it's called deep. So the first figure used there is a neural network in the 80s and 90s. They typically had one layer. There were already sufficient mathematical theorems saying that this is a universal approximator. You can do all kinds of things in principle with that one hidden layer. Deep networks have many hidden layers, and that's really a cartoon of a deep network. And I was limited by the width I had available to me. Think of a deep network as having many, many more layers than this. And so the question really is, what is this success due to? Could it be the network architecture? As I said, there's more layers. That's really the main innovation, or I don't know if you call it, but that's the difference. They're convolutional. most importantly, they're highly over-parameterized, and I will speak to this, meaning that there's a lot more unknown weights or parameters in your network than data points. There's some change in the nonlinearities. People back then liked these sigmoidal nonlinearities. Now they like ReLU nonlinearities, which are kind of rectifiers. They look like the response of a diode. Maybe it's a network architecture. Maybe it's just the fact that we have more data now and computational power. Back in the days, they could not do these problems. Or maybe it's the algorithms. This one really makes my eyebrows raise because the algorithms are pretty much what people were using back in the day. And if anything, there's been a dumbing down of the algorithm. So there are a lot of fancy convex, non-convex algorithms developed over the last few decades, which have had very little impact in deep learning. They're using the very simplest, most basic thing you can think of. And so that cartoon is, I think we're really at a stage, it is the parable of the, blind men in the dark with the elephant. But and so you can think, maybe the answer is really some combination of these. But as I was thinking about it, there's a more important question, which is not why deep learning works, but rather why does deep learning not work? In other words, it should not work. And again, I'm not saying this to be glib or facetious. And the reason for this is that deep learning kind of contradicts at the very beginning the basic premise of conventional learning theory, which is do not overfit. And so it comes under different guises, Occam's razor, curse of dimensionality. A picture I'm sure you're all familiar with is insane polynomial fitting. If, say, here, this green curve is some cubic polynomial, and these are samples of it, they're a little bit noisy, so they don't perfectly sit on the polynomial. And you would like to learn this third-degree polynomial. If what you do is, fit it to a ninth-degree polynomial, you can perfectly fit these data points. But, if I'm queried, somewhere else, they don't really predict what should happen because they're overfitting, okay? And so deep networks take this overfitting to a comical extreme because you're often orders of magnitude. It's not 9 versus 3. It's typically millions versus thousands. So you have thousands of data points, but you have millions of parameters. And so they should overfit and not generalize, but they do. That's what the experience is. And there are these series of papers that show something very counterintuitive, that the larger you make the network, typically the better they behave. They even generalize better. And so what I want to begin to think about and perhaps address in this talk is why on earth this is happening. Okay, so I don't know about Scientific American level talks or the absence of equations, so I will have some, but it's not too serious. So the setting for deep learning is supervised learning. Okay, and so what that means is you have, vectors, feature, or whatever, and you have labels. So think of having images, X, and labels. This is a cat, this is a dog, this is an airplane, and so on. And you want to kind of learn this. So if you're presented later on with another image, you can classify it. And so you assume that you have some parametric model. Think of this as being your network, to which you apply your inputs. It depends on some parameter or weight vector W in some high dimension P. I have n data points, say. And I want to learn this W so that whenever I put in my X, it reproduces the right label. So that's what I want to do. In practice, how you do that is you look at the difference between what this, say, deep network outputs and what the label is. You have some loss function to measure how much error there's there. This is typically quadratic. You just square the difference. And then you sum overall data points. And so what people ostensibly try to do is to minimize this cost function. And it's nonlinear and non-convex and all kinds of things like that. But as I said, when they attempt to minimize this, they use the simplest thing you can probably imagine, which is called stochastic gradient descent, and I'll speak about this a little bit. And so think of these as being estimates of your weight vector as you're doing learning. So this is your estimate, say, at time I, when you've seen some data points. And so what you do is you update along the negative direction of the gradient, not of the entire loss function, which is why this is not gradient descent, but the part of the loss function that depends on the current data point which you're trying to train with. So when you train it each time, you do it based on the current data point. You're kind of oblivious to all the other data points and do it in this particular way, okay? So this is a very simple algorithm. Goes back to Cauchy. Cauchy is the one who invented gradient descent. I'll say a few words because I think it's an interesting story. So the first interesting thing about this is that Cauchy did this when he was 58. So that is good news for me. There's still hope for me. So that is the first thing I took away from this. The other thing about Cauchy is, so he was considered the most rigorous mathematician in his time. And so with gradient descent, it depends on where you initialize and what you choose as the step size, and it may or may not converge. He was aware of all of that. It was a little embarrassing, I think, to him. So at the beginning of his paper, he says, I'll restrict myself here to outlining the principles underlying my method with the intention to come over again the same subject in a paper to follow. So there is no following paper. And I think he realized that this was harder to do, the analysis. So maybe not, we'll see. But anyway, so that's gradient descent. And so stochastic gradient descent, which does this measurement by measurement, is first due to Robbins and Monroe. This is Harold Robbins. I couldn't find a picture of Monroe, but it's been rediscovered multiple times by Frank Rosenblatt when he was looking at his perceptron. Widrow and Hoff did it in a linear context where they called it LMS, least means square. Hoff, incidentally, and maybe there's a Carver connection, is the inventor of the microprocessor, so I think that's what he's holding there. And then Paul Werbosch is probably the first person who applied it to multi-layer perceptrons. And there's other people. It was rediscovered by Rumelhart and McClelland and other people. Okay? So what is it that this algorithm does? Again, I don't know how much math I should go into. There's a way to look at it in terms of, at each step, this update is optimizing something. So you have a current estimate. You try to stay close to your current estimate in Euclidean distance, but you also try to align yourself with the direction of the gradient. That's one way to look at it. It's not very insightful. So something I did in my thesis more than 20 years ago now was to have a global, and I won't go through what this means, there's a global conservation law that this algorithm has, which kind of maps your initial unknown or lack of knowledge about the true weights to what it is after running m steps of the algorithm, and some terms that have to do with the energy of your prediction errors. I won't go into it, but this is really what I use to prove a lot of the results that I will show you in a moment. There's a generalization of this, which I think is very important. It's called mirror descent, stochastic mirror descent. Was introduced by Nemirovsky and Yudin in '83. Again, I could not find a picture of Lev Yudin. And so what he does there's a slight difference if you look at the recursion that he uses. So they start off with some what they call potential function. It has to be differentiable, so I can take gradients. It has to be strictly convex. If you don't know what that means, it's convex, I guess everyone knows. Strict is a little stricter, I guess. So this is the update. And so rather than update the weight vector, you compute the gradient. So you update the gradient of the potential at the weight vector, okay? And this is what it is. And because you have strict convexity, this map is invertible, and so you can actually invert this and find the weight. That's why you really need strict convexity. And if you use a square as your potential, which is strictly convex, the gradient of this is just W, we recover SGD. So it's a generalization of SGD, and I've never fully understood why they actually introduced this, but bear with me. So I'm going to, again, these are digressions, but I will do them nonetheless. There's something important here called Bregman divergence, and I want to tell you what it is, because I wish I had known this when I was doing my thesis. I did not. And so what is Bregman divergence? It's some function that depends on two variables. And so what it is you take this convex potential that's differentiable. Think of this as being your convex smooth function. And I look at the value at W, and I subtract from it the first order approximation generated at a point W prime. Okay? So with a convex function, the first order approximation is a tangent, and convex functions have the property that the tangent is always below. And so this difference between the function and its first order approximation, which is just evaluated W, this is like a Taylor series expansion, is always non-negative, unless the two variables match, which is this point here. So this is an automatic way of building some kind of distance measure from a convex function, okay, by subtracting out the first order terms. And so, for example, if you start off with a quadratic, what you get is the squared Euclidean distance, but you can choose other things. You can take the negative of entropy, which is again convex, and you get something called KL divergence, for those of you who have heard of this. Why am I saying this? So Bregman divergence is this beautiful thing because it shares properties of quadratics. You have this convex function, and when you subtract over the first order terms, you're left with quadratics and higher order things, and so it behaves like quadratics. From high school trigonometry, there's a law of cosines I'm sure you're all familiar with. There is a counterpart with Bregman divergence. From high school algebra, the first time they showed you how to solve a quadratic equation, you probably completed the squares. There's a completion of squares that holds for Bregman divergence. And as a result, you can generalize the properties for SGD to mirror descent. So here, rather than minimize, say, the Euclidean distance between W and WI, you do it in Bregman divergence, and there's a Bregman divergence conservation law as well. Anyway, so that was a little bit of a digression. Let's go back to this deep learning thing. Okay, so again, if you think in the 80s and 90s when people were trying to train these networks, they were using conventional learning theory. They were always under-parametrized, so they had more data points than parameters, and they were looking to find this global minimum. We heard in the previous talk, in the Ising model, that's an example where you want to find the global minimum. And it's hard. And so it's akin to finding a needle in a haystack. Okay? In deep learning, it's the other regime, or is it comically so in the other regime, because we have many, many more parameters than data points. And so there's infinitely many weight vectors that actually interpolate the data. That, just like this high degree polynomial that can interpolate the data. There's many of them. And so the issue really is, it's not this picture, it's this picture. You throw gazillions of needles into your haystack, and so anyone can pull out a needle. I mean, finding a needle is not the problem anymore. They're easy to find, but are they any good? Okay, so here there was a good needle. We can't find it here. Okay, it's needles galore. And so what I want to say is that SMD actually finds special needles. Okay, so to describe this, before I do the whole shebang of a deep network, let's look at an over-parametrized but linear model. Okay, so I'm going to assume that my model is just a linear combination of this unknown parameter, but I have, again, many more parameters p than data points n. Okay, so the question is, if I run this SMD or I run SGD, what does it do? And so this is what it does. So since these are linear equations, the set of weight vectors, what I called script W here, that interpolates the data, of which there are infinitely many, and it's a very high-dimensional object in general, here becomes some kind of affine subspace. So it's a linear subspace, if you will. And so if I initialize with W naught my algorithm, what you can show is that you converge to something that interpolates the data, so you end up on this line, if you will. But it's a very special thing. It's the thing that minimizes the distance between W naught and this subspace in Bregman divergence. Okay, so it finds the closest path in Bregman divergence, the closest point. And in particular, if you initialize this W naught with something that would have minimized your potential without any observations, say in the two-norm case, if you say initialize with 0, then it minimizes the potential. Okay? So this is now called implicit regularization. It's called implicit regularization because we had no intention of doing this. We just had this algorithm going back to whomever, and we're running it, but it turns out it has this property. It minimizes this Bregman divergence. Okay? And you can choose any potential you want. So SGD minimizes a two-norm, but if you want to minimize something else, there's a recipe to do that. Okay? Now what about the nonlinear case, which is what we encounter in these deep networks? So it's a little more complicated. So because it's nonlinear, this set of points that interpolate your data is nonlinear. And again, when you think of this is very highly dimensional space of points that interpolates your data. It looks something like this, but it's the same thing. I have W naught. Ideally, I would like to get to the point that minimizes the Bregman divergence. In the nonlinear case, you can't show that. What you can show is that if you're close enough to this surface, then you will converge to something that interpolates, and you'll be very close to what you want to converge to. So this is the little o notation. So if you start off close enough, you get really close. Okay? And so this means you have some kind of approximate implicit regularization. And if you stare at this at first sight, you may say, this is not so good. I mean, you have to be close, right? This isn't guaranteeing anything. You're saying if I'm close to this surface, then I'll converge and I do implicit regularization. And so what I want to argue for you is that the blessing of dimensionality is that you are close. Everything is local, because P is huge compared to N. And so we have all, gazillions, as I said, of these needles. And so if you think of a typical neural network with, say, 1 million parameters in it, P is 1 million, and maybe you have 10,000 data points. So the dimension of this set that interpolates your data is 990,000 dimensional. So any point you randomly choose to initialize from will be close to something that interpolates the data. And mathematically, you can say something about the closeness. It's on the order of this ratio, so 10,000 to 1 million. Okay, and so the message is that in the highly overparametrized case, you're almost guaranteed convergence, which is what people see. Whenever they run these networks, they always get to zero training error. Convergence is not an issue. And so, you get regularization, and perhaps with the right regularizer, you'll get the generalization that you want, okay? So that's my message. I don't know if I convinced you. So you might be skeptical and say, is this true? Okay, so we started running some experiments. So we tested this stochastic mirror descent. There are these benchmark data sets out there, something called MNIST, which has characters in it, and CFAR10, which I will speak to. So we did experiments on these. I'll describe the CFAR10 experiments in a second. So maybe I should say what CFAR10 is. So it's a data set of images. There's 60,000 images in it. 50,000 is the training data. There's 10,000 test data. So you test the generalization on those. You train with 50,000. The images are in 10 categories: ship, dog, deer, bird, ship, whatever. And in order to compare with other things, we trained on something called the ResNet 18 deep network. So the 18 means that there's 18 layers in this network. It's a particular architecture. You don't touch the architecture. It has over 11 million weights. Okay, so P is 11 million, N is 50,000. So this is like 200 times more parameters than things. And so the first thing we did was, we chose 4 different potentials, if you will. So L2 is the usual Euclidean distance. L1, we look at the absolute value of the weight vectors. That's what L1 is. It's the L1 norm. L3 looks at the sum of the absolute value, or the cubes of the absolute values. And L10 is the 10th power of the absolute values. This was our surrogate for L infinity. 10 is infinite for us. And so we ran with all of these things. The first thing we verified was the theorem. So in every case we ran 8 different initial conditions around 0. We ran all 4 algorithms, so we ended up with 32 points that perfectly interpolate the data. And we indeed verified that each point was closest to the initial point from which it came in, according to the Bregman divergence that generated it. So we verified, at least with these 32 points, the premise of the theory. So maybe this gentleman here will start smiling after that. But so that we verified. But let me, so I can't really show you an 11-dimensional vector. And so let me show you histograms of these weights, okay? So, and this is an example for one of these initializations, but they all kind of behave the same way. So I'm showing you the histogram. So, and this is the absolute value of the weights. So the true distributions are symmetrical. So this is L1, this is L2, this is L3, this is L10. So the L2, and they all have the same scale. They're between 0 and 0.05. So we initialize around 0, so the weights don't get too big. So these are all data points that interpolate the data perfectly. So when you do L2, the distribution of the weights looks Gaussian, and there's reasons to believe that it is Gaussian, so we were not too surprised by this. The L1 encourages sparsity because it doesn't penalize small or big weights as much. In other words, it likes small weights. These other guys kind of kill off the small weights, so they don't care about them. And so as you can see, this distribution compared to the Gaussian is shifted to the left. For example, we have 300,000 zero-weight vectors here. In the Gaussian, there's maybe around 150,000. So the number of zeros in this network is double. When you go to L3, you see the weights begin to move away from the origin. And at L10, they're clearly away. So they have this strange shape here. So these are, again, they're very different data points. They all interpolate the data. And so we ask the question, do they generalize differently? What do you think? Would these have different generalization behaviors? And so myself looking at this, I had thought that this one is the one who should generalize better because it's more sparse. And we'd all heard of Occam's razor, the less number of parameters, the better. There's all this work on compressed sensing about trying to sparsify. I had worked in the 90s on algorithms for network pruning to kind of sparsify it. This is naturally sparsifying. So I'm saying all this because we got the reverse. So this is the generalization error. So we had 8 initializations. So I have 8 samples of the generalization error. So for each initial point, we generated according to, by either optimizing the L1, L2, L3, or L10, a point that interpolates the data. And then we measured the test accuracy. So bigger is better here. And you see a clear difference. So L1 is the worst. Clearly worse. In all 8 runs, it's worse. L2 and L3 kind of behave the same. L10 is clearly the best. And so this is one where all the weights participate. And the other thing I should say is, so on this CFAR 10 data, the world record is around almost 96%. But that's on much bigger networks and with all kinds of tricks, batch renormalization and skip connections and lots of hard work. On ResNet 18, on this particular architecture, this beats the world record on the ResNet 18 architecture. And so I don't understand this at all. This is also very counterintuitive. Why would this regularization work? So I'll kind of conclude and say a few things about the future work here. So the blessing of dimensionality. Why is it that this thing's working? Is because when you're in the very high dimensional setting, your set of interpolation points is this very, very high dimensional object. And so everything is local. So convergence is not an issue. People have, pretty much whatever they initialize with, they get zero training error. It really matters which solution you're choosing. And that's really where happen chance or beginner's luck or something came into play. So people who are running these algorithms had no idea that they naturally regularize, that SGD in particular, which is what everyone almost uses, minimizes a 2 norm, so it gets a very special solution. People fuss a lot about the loss function. Oh, you should do quadratic, or you should do cross entropy, or whatever. Loss function doesn't matter because you get to zero loss. What matters is the potential. When you're using SMD, what potential you choose. And none of these things was intended. Okay, so if people were using something else, we would not have had, I think, the success of deep learning. And so what are the questions moving forward? So the first thing is, why on earth was L1 the worst and L10 the best? I have no idea. And maybe that's just attributable to this CFAR 10 data, but it's so clearly so that there must be something going on. And in fact, what is a good regularizer? We have now this understanding of the self-regularization of these algorithms. What's a good regularizer to use? And can we do that to create a generalization theory for deep learning that would really assist us, somehow getting to the heart of this black magic, perhaps. I'll end here. Thank you.
So we'll take some questions. I think he raised more questions than he answered. So yeah. You need to get to the mic. Can we pass the mic back up?
So did you apply this at all to non-stationary data, like time series data?
So that's a very interesting question. I am very new to this field, and to me, the way I came to this was kind of, why on earth does this work? So I haven't played around with data that much. This MNIST and CFAR 10 was the first thing. So I'm not really qualified to speak much to that. But I think that would be an interesting. So there are, I should say something about the origins of where the theory behind this comes from. It comes from, I don't know if John Doyle is here, from H-infinity control. And there people can address things like time-varying systems and non-stationary systems and so on. I would assume that if you had time-varying data that you would want to change your algorithms accordingly. But again, I'm not the right person. I don't know what people do, what the state of the art is. But I think this type of analysis certainly can react to the type of question that you've raised, and have things to
Yeah,
answer.
my experience is, having done a little bit of that, you'll find exactly the opposite results. The simpler, the overfitting becomes a real problem.
Becomes a real problem in the non-stationary case.
So that,
Well, speaking of black magic, it's a classic conundrum in machine learning that that image recognizers, face recognizers, do a much poorer job on black faces, African American faces, than on Caucasian faces. Is there anything that you've seen in this that could help explain that?
So these are all very good questions for someone else, I think. But the only way I can react to that, it's probably an artifact of the data that the machine learning algorithms are being exposed to. So they probably see more of Caucasian faces than they see of others.
Question. So in machine learning, which has been called model making for decades, one of the principles is that the best model is the one with the simplest number of parameters. What has happened in that concept? Is deep learning just ignoring that concept?
I think the short answer is yes, which is why I had my very first slide. That's why this is so counterintuitive. Why I brought up the Occam's razor kind of thing. Why this L1 regularizer behaving worse than the L10 is also baffling to me a little bit. So I think maybe it's really the issue that counting parameters is really a poor man's way of, or poor person's way rather, of seeing what the complexity of a network is. There might be other measures that are quantifiable in other ways. It's not just counting parameters, but it might be some other property of these parameters. But I think clearly what's going on here, in my view at least, is that these additional dimensions are making the optimization problem easier to solve. Okay? So I kind of remember in the 90s when I was a grad student, we were trying to train these networks that were under-parameterized. Because it's nonlinear, every initial condition would give you a different solution. We'd have to run thousands of initial conditions and choose the best one. That problem has kind of gone away here. Typically, every initial condition you choose with will take you to zero training error. So one advantage, I think, of this explosion of the search space is that. And so I think once you put that there, I think it's a question of what is the right algorithm to choose the right solution in this gigantic search space, which is what I was trying to allude to here. We need to figure out what the right regularizers are and what is the generalization theory for that. And so this plot that I wanted to show you, well, I did something else. Anyway, it showed up nonetheless. Really shows that there is a difference between points. So these are 32 points that all give you zero training error. And there's a clear difference in the generalization error. So classical learning theory, if you look at things like VC dimension that come out, what they try to do is relate the training error you get on your data set to the generalization error. And people had noticed earlier, when they started looking at this in the context of deep learning, that these gave you very pessimistic bounds. And the reason is they have to kind of bound the generalization performance of any algorithm or any data point that gives you zero training error. And there's many of them. And so what you really need is a generalization error that can kind of predict the generalization error based on the algorithm that you're using, and perhaps things like the network architecture. Mm-hmm. And so this is, I think, some empirical evidence of the fact that what you converge to actually matters. I hope that somewhat.
Okay, we'll take yeah, come on. Come down. He's got a burning question, yeah.
Yes, I think you said you have verified that the result of training is actually find the closest way to the initialized weight. How can you verify that there are no other optimal ways closer to the initializer?
That's a good question. So first of all, my theorem doesn't say you find the closest one in the nonlinear. In the linear case, you can prove that. In the nonlinear case, you come to something that's close to the closest point. All we verified, so what we verified experimentally is on these 32 points, and 32 points is only 32 points out of gazillions of points, that we converged to the one that was closest among those. But the claim is not that you converge to the closest. The claim is that you converge to something that's close to the closest.
Close to the closest. Yeah, okay.